Okay, so let's talk about angular momentum to start with here. Okay, so if we have a Cartesian axis, let's look at a planar situation with the xy plane. And let's say in the xy plane, we have a vector that represents our momentum, mass times velocity. Again, this is on the xy plane. Then our angular momentum can be calculated by taking and measuring the perpendicular distance about some point, say O. So our angular momentum about O, which we often represent as h sub O, equals mass times velocity, or momentum, times this distance d. So we can think of this as if there's a particle here moving along some path on the xy plane. Let's draw a path a little more reasonable. Say it's a path like this along the xy plane. And this is a scalar representation of our angular momentum. So the momentum will be in the direction of the z-axis using the right-hand rule. So let's look at example 1512 here. And here we have a box sliding down a curved ramp with some initial velocity, and we're interested in this angle theta. So let us find the angular momentum about point O. Well, this is just simply, we can let's look at a free body diagram, what's going on here. So this is say the t direction. This is our normal direction. So we'll have a normal force on our box here, and we will have a weight on our box here. This weight makes an angle of theta here. So then our angular momentum equals mass times our velocity times the radius r, and this has a radius based on the distance, essentially the perpendicular distance to O, and that will be in this direction. So by convention, since it's clockwise, we might call that a negative. Since using the right-hand rule, positive is counterclockwise, we might call that a negative value. Okay, that's the first part of example 1512. We need to look at a more general situation here. Now, let's think of a particle moving on a path in space, 3D space. Now, so our particle will have a momentum, say mv here, which is a vector now. So if we're going to figure out what our moment of that vector is about O, we're going to have to use cross product. So our angular momentum about O is going to equal some position vector, and we can take this line of action past this point here for our direction of our position vector r, and we can just take the r and we can cross mv with it. So that will, right hand rule, you'll take R and cross MV with it in this direction, and that will give us a vector that points in a general direction with 3 components, like this. And of course, this can be moved down to here. One way to perform that operation is to take the determinant ijk, calculate the determinant ijk. These are the unit vectors with the components in the different directions, rx, ry, rz of first the position vector, and then next the other vector, which is our momentum. So mvx, mvy, mvz. So when we evaluate that, that equals, and this is what you get when you evaluate that determinant. I think the quickest way to do that is to use a cofactor method, and I think I'll demonstrate that in an example here later. And then that is just our angular momentum about O. Okay, so now let's relate moments of forces, or let's relate forces to angular momentum, and we do this by taking a moment of the force. So let's say we have a particle moving on a path in space, and we have an applied force on that, or a resultant force, let's just say a summation of forces on that particle in some arbitrary direction. Well, we can still shoot a vector r to this. And let's relate these forces to angular momentum. We can do this by considering Newton's second law. Which says that the sum of our forces equals mass times acceleration, which essentially is the same thing as mass times velocity dot, or the rate of change of velocity, dv dt. So if I'm looking at these forces and I want to sum their moment about O, what we're going to end up with is R cross F, and that is going to equal R cross, so if we take R and cross F, we got to take R and cross M V dot. So what is this M V dot stuff going on here? Well, let's look at what our rate of change of angular momentum is. That's the same thing as taking the derivative with respect to time of our angular momentum, which equals the derivative with respect to time of R cross MV. And if we apply the product rule to a cross product, we get R dot cross MV plus R cross MV dot, completely analogous to the cross product of a scalar. And we see that this first term here of R dot cross MV is just R dot cross M R dot. So these two vectors are in the same direction, and if you have a cross product in the same direction, this is going to equal 0. So this equals 0. So that means then that H dot, H0 dot, the rate of change of our angular momentum is just r cross m v dot. So plugging h0 dot into the above equation, you essentially are going to get the sum of moments of our forces about O equals h dot about O. So the sum of forces about O equals the rate of change of the angular momentum. This will be useful to us. So let's use this to finish the second part of example 1512 and find the acceleration of the box. So now we'll make use of this free body diagram. And let's begin by summing moments about O equals h0 dot. So summing moments about O means we'll end up with W times the sine of theta, which is the component of W that is perpendicular to theta, and then multiplied by the distance r. And then this equals the derivative of or h0 dot that we derived above, which is mass times velocity dot times r. Okay, and then in this formula we can cancel quite a bit. W we can think of is mass times gravity. So we can cancel out m, and we can cancel out r here. And we're left with g times sine theta equals v dot. And this is our acceleration in the tangential direction. Note, we could use our past methods, and we could sum forces in the tangential direction equals this, and cancel our m here, and we get the exact same relationship. Okay, moving on to section 7. All right, since we have this relationship, we can look at this differential equation and separate variables and solve it, going from T1 to T2 over here, and H01, or the angular momentum initially, and the angular momentum final. You'll recall this is similar to what we did before with forces and momentum. This leaves us with this relationship, H01 plus the summation of the integral from T1 to T2 of M0 dt equals H02. This then is our angular impulse instead of a regular force impulse, and that is just the area under the moment curve. Notice that note that the integral of our moment about O is just the integral of r cross f, the vector that results there. And for summation, or for a system of particles, we just have this relationship. Then in summary, we have these two equations. The top is the linear impulse momentum, and the bottom is the angular impulse momentum. So for a scalar breakdown of these, we then have three relationships, one in the x, one in the y, and the angular momentum about the z-axis. We have linear momentums about the x and the y-axis, or rather along the x and the y-axis. Finally, note if there are no angular impulses, obviously that cancels out, this will cancel out, and we end up with the initial equals the final angular impulse.